Okay, good morning. Today we'll be talking about hierarchy theorems, mainly time hierarchy theorems. So I'm going to start actually by reminding you about the basic time hierarchy theorem for good old deterministic Turing machines, which hopefully you've seen before, but we're going to look at a few details of it. And we're going to end with a more difficult theorem, which is actually surprisingly important in complexity theory, which is the time hierarchy theorem for non-deterministic Turing machines, which requires quite a different proof than the one for deterministic Turing machines that just uses diagonalization. Okay, so I'm going to start by telling you about the time hierarchy theorem, the basic one for regular old multi-tape Turing machines. And I'm going to do it at a high level to start, because this is a theorem where the idea, which is diagonalization, is not too complicated. But there's actually several technical details, some of which are kind of annoying, that you need if you really want to do the proof very carefully. So I'll start with a high-level description, and then we'll talk about all the issues afterwards. So here's a statement at a high level of the time hierarchy theorem. So it won't be fully detailed, as you'll see in the next few symbols. So let's assume that you have two running time functions, t1 of n and t2 of n, and just assume that t2 of n is noticeably bigger than t1 of n. You know, certainly t1 of n should be little o of t2, but maybe even a little bit smaller. If you want, for example, just to keep something really concrete in your mind, you know, this could be maybe n squared. Maybe you can't read that, but it doesn't matter. And this could be like something noticeably bigger, like n to the 6th. Okay, and then the theorem is that there exists some language such that L is in the larger time class. You can solve it in t2 time, but not in t1 time. Okay, so the high-level message is that more time really buys you more power. If I give you noticeably more time, then you can decide like strictly more languages. Okay. So as I said, I'm going to now sketch the high-level idea of this theorem's proof, which is diagonalization. So the first thing that the proof requires actually is, you know, just to fix some encoding scheme for Turing machines. So you need like any simple scheme for like having, you know, a way of writing down a Turing machine description in, let's say, bits. Okay, and like any normal, plausible, simple way of having a system like that is fine. You just need to fix one. So fix some simple, straightforward mapping. I'm actually going to describe the mapping in the other direction, like a mapping that takes a string and outputs the Turing machine that it is describing or encoding. So I'll use some funny notation. DTM stands for deterministic Turing machine. That takes some strings, it could be just 0, 1 star binary strings, to the set of Turing machines. And you know, all you really need out of this scheme is that like every Turing machine has at least one, you know, encoding. There's some string that maps onto that Turing machine. Well, actually, you need a bit more than that, as we'll see. And you might also ask, this is an annoying issue that always comes up in complexity theory when you're encoding objects by strings, as you kind of have to do. Like, what happens if you apply this mapping from strings to Turing machines to like a string that's like malformed, that's like not the standard encoding of a Turing machine? In that case, just assume that it outputs some like default trivial Turing machine that, I don't know, immediately rejects. Okay? So if you give this some garbage string, it outputs a default Turing machine. Yeah?
Why in this case we are not defining and mapping from Turing machines to the strings? Because it's then being sure that every Turing machine has an image, and also we do not take care of the garbage.
You'll see in a second. In fact, ultimately, we want the fact that we're actually going to use the fact that every Turing machine has multiple encodings. But you can have this in mind. I mean, you should have in mind like a canonical way to go the other direction. That's the more normal thing, actually, to take a Turing machine and like convert it to a string in a normal way. So this is kind of the inverse of the mapping, but like extended so that it can take as input any string, even if it's not in the range of the encoding mapping. Even if it takes in a garbage string, just have it output, this forward mapping output some default Turing machine. And that's convenient to have so that like every string can be considered as the encoding of a Turing machine. That'll be useful. But notice already that already gives you the property that some Turing machines have more than one valid string encoding. Because let's say if you really are the trivial Turing machine that always rejects, then you have your proper encoding, plus any junk string is also an encoding of you. But that's fine. OK, so such that, well, among the other things I described, we want that for all Turing machines M, there exists an X such that the encoding of X, the decoding of X in some sense is M. Actually, as we'll see later, we need to upgrade this so that it's kind of a spoiler that infinitely many strings decode to the same M. But let's just ignore that for now. OK, so that's some basics. So now we need to define this language that can be solved in t2 time but cannot be solved in t1 time. And unlike how things sometimes go, where you just say, like, here's the language, and you describe the language, it's done a bit indirectly here. What we're going to do is describe a Turing machine that runs in t2 time. And then we'll just say, whatever strings this Turing machine accepts, that's the language. So we're going to do this by defining the Turing machine that runs in t2 time. And so this part that the language it accepts is in t2 time will be trivial. And the main thing that we have to worry about is that showing that the language it accepts is not doable in t1 time. And what's the idea of the proof? The idea is that this Turing machine that's running in t2 time is going to try to diagonalize against all t1 time Turing machines. It's going to make sure that for every t1 time Turing machine, it does the opposite of that Turing machine on some string. Okay, so as I said, we're going to define this language via time t2 of n Turing machine that decides it. Okay, so let me put up here the key thing, the magic Turing machine D for diagonalization, I guess, that does the job. So D takes as input some string x. And here's what it does. First, it sort of lets, in its mind, M be the Turing machine encoded by its input string. OK, so it interprets its input as a Turing machine. And it's going to simulate M on X, so sort of on its own description, for, well, now I want to do it for basically t1 steps. But I'm going to do it for a number of steps that's a little bit bigger than t1, sort of just in case. You'll see why eventually. OK, so for a number of steps, I'll call t sub 1.5 of x. OK, and what's the deal with t sub 1.5? It's just so that I want t1 to be sort of, sorry, t1.5 to be sort of between t1 and t2. OK, so already you see we're getting to a little bit of technicalities here. OK, so do that simulation. D is going to do that simulation. And then it'll just do the opposite. OK, this is the diagonalization aspect. Then do the opposite of what M does. In other words, if M accepts, then D will reject. And if M rejects, then D will accept. And of course, there's a third possibility. There's the third possibility that M, after t 1.5 steps, hasn't accepted or rejected yet. In that case, it's actually not going to matter what D does. It doesn't matter what D does in this case. But for concreteness, you have it do something. So let's say if neither, so I said it doesn't matter, but whatever, D can accept. Okay, so we'll see in the proof it doesn't matter what you do here. Any questions so far? OK, that's D. OK, so let's take a look at D's action, still at a high level. OK, so what does D mainly have to do? It mainly has to carry out this simulation of a Turing machine. So it's got the description of the Turing machine, its state, transition table, and everything. That's what it got up here. And it's got the input x. It's got to simulate it. It's got to simulate it for this many steps. So maybe there's a little bit of overhead in simulation, but that's why I'm imagining T2 is somewhat bigger than T1.5. So we'll just assume that this can be done in T2 time by D. Okay, and I allow myself right to assume here because we're just talking at a high level so far. Okay, we'll come back to this later. But naturally, it's not too hard to simulate a machine for a fixed number of steps without too much overhead. So that's what you do. Okay. All right. So that's it. So then, as I said, the language L that we're looking for is just whatever language is accepted by D. And so the fact that L is in time T2 is, as I said, done. I mean, it's by this fact. Okay, so the main point is that we have to show that it cannot be decided, L, by any T1 time Turing machine. So really what we just need to do is say, take any T1 time Turing machine and show that there's some string where Q and D do the opposite thing. And that means that Q is not deciding L correctly because it's making at least one mistake. So let Q be any Turing machine running in, at most T1 and time. That's what we have to guard against. Okay, and what will be the string where Q and D differ? Yeah?
Q itself.
Yeah, so it'll be the string that encodes Q itself, or any string which encodes Q. That's sort of the point here. So consider any X such that Q is the encoding of X. Okay. So we said before, one fixed Turing machine might have several encoding strings. That's fine. Just take any string that is an encoding of Q. There's always at least one. And let's see. Oh, I hope I can end the proof right here. That would be perfect. Cool. OK, so Q of X. Q, when you actually run it on this string, what do we know about it? We know that it finishes in T1 of length of X time. Well, maybe. We'll come back to this point. But yeah, we know that it finishes in T1 of X time because it's a T1 time. Actually, no. So far, what I've written is all fine. So it finishes in T1 of length of X time. And we know this is less than T1.5 X time, noticeably less even. OK, so that means, what does that mean? Therefore, like when you run D on this X, D figures out that X encodes Q, and it starts simulating Q of X for this many steps. Q actually finishes in this many steps. So the point is, like, this is fine in the sense that this doesn't happen. Like Q on X in this simulation actually finishes. So everything is cool. It finishes the simulation. And therefore, it does the opposite. OK, so therefore, Q on X is different from D on X. OK, and so Q gets this question, X in L, wrong. OK, end of proof. So in other words, Q, which is any T1 time Turing machine, does not decide L. OK, any questions about the proof? Yeah.
So is the big O baked into the word time on that second last line there?
OK, good. So that's issue number one with the proof. So there is a bug in this proof, which is that this is all correct. I let Q be any Turing machine running in time T1 of n and showed that it won't decide the language, L. But according to our definitions, and we like our definitions, that does not actually show that the language is not in this class. Because this class is all the languages solvable by a Turing machine that runs in big O of T1 time. Not just exactly t1 time, but big O of t1 time. So actually, and we like that. We don't want to change that definition. So we have to work a bit harder in the proof. Let me just write that on the board. And that makes things a little bit tricky, because we have to not just diagonalize against time literally t1 of n, but this allows for time basically c times t1 of n for any constant c. Okay. Really for sufficiently large n, but it's always the case that for sufficiently large n, you can kind of build it into the constant c by making c bigger. So this is actually trickier because we have to diagonalize not just against time t1 of n, but against any large constant multiple of t1 time. So that's certainly one reason why we actually need t1.5 to be sort of noticeably bigger than t1. Okay, it's not just enough that it's strictly bigger, but it's clearly going to have to be sort of fundamentally bigger, little omega of t1. If t1 is n, this thing had better be something that grows strictly faster than n, like n times log n or something. So that at least has the potential to cover c times n for any constant c. Okay. I'm actually going to not dwell on this point too much, because it's in the proof of the original theorem, which maybe you've seen, or it's in Sipser and Arora and Barak, but I want to talk about it a little bit without totally going over it. So in particular, we're certainly going to need in this proof sketch that t1 of n is little o of t1.5 of n. Well, we don't have any hope of covering diagonalizing against c times t1 for all capital C. Now, here's where there's really kind of a bit of a catch. I shouldn't have erased this panel, but anyway. Even this is not quite enough, because I'm going to say this in words. It's really not enough for the diagonalizer to ensure that every t1 time Turing machine Q, or big O of t1 time machine Q, differs from D on at least one input. And the reason is, this running time t1.5 is only if let's say it's n squared and this is big O of n, it's only bigger than big O of n for sufficiently large n. So really, it's not enough to beat a big O of t1 or a big O of n time Turing machine for a single n, for a single input of length n, because that input length might not be long enough to get into the regime where this running time is beating this running time. It's a bit of a technical point, but what it really just boils down to, if you want to review the Sipser proof, that you just need to make sure that your diagonalizing Turing machine is beating or differing from Q on infinitely many x's, so that you can be sure that Q is failing on arbitrarily long strings, not just one single string, because that if it's just one single string, that might be a string that's so short that you're not in the regime yet where 1 times n squared is bigger than c times n, for example. Okay, so let me just say that in words, and you can think about it a bit more carefully if you like, but long story short is you also need that Q is equal to the encoding of x for infinitely many x's, or really for arbitrarily long x's, which is the same thing as for infinitely many x's. But that's OK. It's not hard to arrange. The way you can do it, and the way it's done in all these proofs, is you just take any standard scheme for saying, OK, here's how you map a string onto a Turing machine, just some kind of file format for Turing machines. And then you just allow any number of junk characters at the end. Take some junk character I don't know, $, and just allow any string with any number of $signs at the end to be an encoding of the Turing machine that's just the regular part of the string. Okay, so these are just sort of stupid Turing machine tricks. Well, it's sort of stupid big O tricks, but it's something you technically need to do in order to make this proof work. Any questions about that? It's a bit of a technical point. If you don't quite get it, it's OK, because it's not the most important thing in the world. But we need that. OK, so the point of this is that sort of, c times t1 of x strictly less than t2 of x, sorry, 1.5 of x, eventually kicks in. Okay, so that's issue 1 with this proof, which we have solved in words. Issue 2 with the proof, it's not like a bug so much as something that just needs to be delved into, is this. So we assume that we can simulate this Turing machine. We have this description of a Turing machine in our hands, and we have a string x in our hands. We want to simulate m on x for like this many steps. And we're allotting ourselves t2 of x steps. So we have to see, is that enough? Okay. And there's an issue here which is actually kind of similar to this technical issue 1 that I was just discussing, which is that, you see, we need D to be a fixed, order T2 of n time Turing machine. D that can simulate any time order t to the 1.5 and Turing machine m. And okay, so we need like a universal Turing machine here that takes as input a Turing machine description and a string and simulates it for some number of steps. So we need this universal Turing machine to actually be able to handle several potentially slightly difficult aspects of this job. So it must handle m's any constant number of, right over here, you see, one thing it has to handle is that m could have any constant number of states. That's okay, that's fine. I mean, m, this Turing machine gets m's description, it could have like 1 million states, whereas, the D itself has some fixed number of states, like 100. But that's okay, there are universal Turing machines that can sort of simulate any arbitrary Turing machine with many states, themselves. So obviously they have to like write m's states onto the tape. They can't like sort of simulate m states by their own states, but that's fine. It also has to handle the fact that m could have an arbitrarily large but constant size tape alphabet. So again, D is kind of like got a universal Turing machine inside it with some fixed tape alphabet, maybe 10 symbols. But M is like any old Turing machine, so it could be using 1,000 tape symbols. Again, that's fine. You do the obvious thing, which you've seen before when you first study Turing machines. You encode M's large tape alphabet with your own small tape alphabet, and that's fine. You can encode a tape alphabet of size 1,000 with 3 tape symbols for an alphabet of size 10. So this will also only incur like a constant slowdown in some sense. I guess what I'm getting at here is I want to like think about if like we have to do this many steps in our simulator, like how much slowdown is that going to incur? There's one more thing that M could have a large constant number of, which makes things actually tricky, and that's tapes. Okay, so recall that we said our default Turing machine model is the multi-tape Turing machine model, and that's a good choice. And it's a choice that's different from, let's say, the one in Sipser, where he says we're going to use one-tape Turing machines. Well, those are kind of annoying one-tape Turing machines, so we want to talk about multi-tape Turing machines. But we have the same tricky phenomenon here, which is that, D has some fixed number of tapes, like 2 or 3 or 4. But like M could have kind of any constant number of tapes. It could have like 1,000 tapes. And so this Turing machine has to simulate like an 1,000-tape Turing machine on like a 3-tape Turing machine. Now again, as you know, like that's not like a insuperable problem. Like it's like stupid Turing machine tricks. You'll have to encode M's 1,000 tapes all onto your one, like maybe or 1 or 2 tapes of D. In some kind of parallel fashion. You'll have to like increase the tape alphabet and do encoding tricks and so forth and so on. But this is actually a little bit expensive. Okay, so if you've done this exercise before in your life, you might know that like simulating a constant tape, a k-tape Turing machine by a 2-tape Turing machine is doable with some slowdown. I say 2-tape Turing machine here because it's really painful to do anything on a 1-tape Turing machine. So we'll definitely assume that like D has got at least 2 tapes. So what's easy, or not too bad, is that like you can do this for time t in time order t squared. And roughly, why is it t squared? Well, let's say you're simulating some 10 tapes. They all have their heads in different positions, right? But you only have like a fixed number of tapes, and their heads could all be up to like distance t apart. So like even to do one time step, you might kind of have to like walk distance t on your own tape to go check where all the heads are, so you know what to do next. So that's fine. But what that basically means is in this theorem, we'd have to take t2 to be the square of t1.5, which is a bit of a drag. It's kind of fine if you don't care about too much about quantitative details, but you may care about quantitative details and really try to make t2 not that much bigger than t1.5. So what you need for that is like some crazy algorithms data structure thing that does this simulation very fast. And back in the 60s, people programmed Turing machines for a living. And in particular, Henny and Stearns, in the summer of '64, they did this kind of cool result. They did it in time order t log t. So I'm not going to do that proof. It's not easy. It's in Aurora Barak if you want to read it. It's like that block respecting thing on your homework, but like much more annoying. I mean, you have to do lots of tricks. In particular, what's kind of interesting about it is you really use like amortized analysis. So it's not like you do every step here in time like order log t. Like you really have to kind of bunch up steps and so forth and so on. Like the trick is somehow like you arrange the k tapes here so that it's like the head always stays in one position, and you shuffle the tapes around like underneath it, so the heads are always in the same place. But then the heads, you can't just copy the whole tape in one step, so you kind of copy it in pieces and you divide it into like segments of size that are like powers of 2, and it takes a paper to do it. So we're not going to do it, but we're going to take this result and be happy about it. Okay, and so because of this is the best thing we know. It's actually unknown if you can get it down to order t. It's an open question. But because of this, you need in this algorithm to take t2 to be like big O of t 1.5 log t of 1.5. Okay. And so you just counting up the things that we decided we needed. We need this, and we also need this. Okay, and that leads us to, almost to the statement of the full time hierarchy theorem. There's one more issue, which is you probably recall if you ever studied this proof. It's like the most annoying issue. But the simulator basically needs to be able to count how many steps it's doing. So it needs to be able to clock off t2 of n time. In other words, the simulator eventually is going to like time itself and go for t2 of n steps. So like on input of string x, it needs to figure out what is t2 of length of x. And normally that's kind of trivial. If like t2 is like n squared or something, you can do this, you count x, this is length, that's log n bits, you square it, that's easily done. But like theoretically, you can't just let t2 be any insane function, because it might be like any crazy function that's like, it's just extremely hard to compute. That's ridiculous, but you just have to use this as a very technicality. So there's a definition involved here, which basically is like a mantra you just have to always put at the beginning of proofs, that all your running times are so-called time constructible. So this Tn is a time constructible function if there exists a Turing machine that on inputs of length n writes out, t of n symbols, let's say ones. So it writes down 1 repeated t of n times in order t of n time. Okay, so you want that, you can compute the number of steps you're going to run for, t2 in this application, in like not much more than t of n time. In fact, almost all like normal time constructible functions you can compute in like order n time, because like the main work is just counting the length of the input. So basically every normal looking function you ever encounter has this property, but like you kind of just have to always say it when you're stating theorems like this time hierarchy theorem. Yep?
Are time constructible functions dense in like, I mean, you could consider an ordering by like little o and
probably not. Well, I mean, like there's functions that like are not mutually comparable, like with big O-ness. Like these insane things like, oh, if you're even, you have this function. If you're odd, you have that function. So in like the 6 days, they also proved like these like insane theorems where like if you have a crazy, there exist crazy functions t of n such that time t of n is equal to time 2 to the t of n. It's called like the gap theorem by like Borodin or somebody. And these are insane theorems. And they just exploit the fact that these t of n's are bizarre functions that are not time constructible, and like they're not mutually comparable in terms of big O and insanity like that. But like every function you'll encounter in life is time constructible. Okay, so here's the time hierarchy theorem, like official statement. Let t1 of n be at least n. We basically never consider running times that are less than n. And let t2 of n be two things. First of all, it should grow strictly faster than t1 of n log t1 of n. Okay, that's the combination of these two needs that we described. In other words, this amount should be little o of t2. And time constructible. Then the conclusion. Okay, so then there exists an L that's in time t2, but not time t1. Okay, so that's the official theorem. And this is the sketch of the proof. One sec. It's actually also, this log really comes from this part. So it's actually known, they proved these crazy things in the 80s, like, let's say you fix your model of Turing machines to be 2-tape. Like, that's it. Every Turing machine is 2-tape. Then you don't need to do this. You still need actually, you might think you need a log because you have to like keep track of a counter that counts the number of steps you've done so far. But like with some insane tricks, you can get rid of that. And so if you just fix all Turing machines to be like 2 tapes, then like you don't need this log piece, and you get like the perfect time hierarchy theorem. But we don't want to do that. We like to allow any number of tapes. Yeah, Purva.
So just a question about the first issue. The reason that we need infinitely many x's, is that because it can go into the third case? Is that why that's a problem?
The third case?
The third case of the Turing.
Yeah, that's right. Yeah, the fact that it hasn't halted the queue, the thing that you're simulating, even though you kind of expected it to halt because you assumed it was like t1 time, but like it might not have because like it might be so short that, yeah.
If you don't need the counter in the 2-tape model, then does it need to be time constructible?
Yeah, I mean you need to like know how much time you're simulating it for, but then like you do some insane tricks to do the counting. It's like, you write down the counter, it's log t bits, and like you update it every step, but you're only updating the lower order bits most of the time. So like you're dragging that along, you just drag the lower order bits along, and then when you need to update a high order bit, you go back on the tape to find it, and like it's crazy. So I'm not going to get into that, but yeah.
What do you need the t1 and what n equals n?
You probably don't. I don't know. I copied this from somewhere. I mean, you need that like T2. I mean, the dissimulating machine, like the first thing it needs to do is like count the size of the input. So it needs at least n times, surely. Now, I guess probably, I didn't think about this carefully, but probably if you assume that T2 is time constructible, it almost like has to be at least n. Because how is it going to construct it if it can't even compute n? So maybe this hypothesis is not necessary, but it's not going to We're not going to really worry about it for less than n. Actually, also it's false in this. I mean, for smaller things, in the sense that like time like log n is the same as constant time. You can prove that. Like it's the same as regular languages. So it definitely sort of fails for running times that are like noticeably less than n. Yeah.
Does it actually matter that T2 is time constructible, or do you just need T1.5 be time constructible? Like, is it possible that like T2 isn't time constructible, but you just like hard code in some T1.5 that's smaller than T2 that is time constructible and things still work out?
No, I think you need. I mean, first of all, in life, like all the functions are going to be time constructible anyway. But this is, I guess, the time in our life when we should discuss these things. I don't think so, right? Because the thing that the simulating algorithm really needs to do is run for T2 time, because it has to be able to simulate T1.5 steps, which so it needs to be able to clock itself for that amount of time. So I think it's that the biggest thing here, T2, has to be time constructible. All right.
So, like, even if the model with the multi-tape Turing machine,
Yeah.
we consider two times that are closer to each other in terms of log.
Yeah.
So, do we know something about that? Like, what happens in this case?
You have not read problem 3 on the homework yet. No, just kidding. Yeah, you can actually improve this theorem in certain cases, even in this model. So on the homework, like, you're going to consider the case where T2 is like n squared, I think. And so the time hierarchy theorem, as stated here, only tells you that there's something in time n squared log n, basically, that's not in time n squared. But you can get that down to you can actually get it down to like n squared times log to the 0.0001 n by further tricks that use this theorem. So you'll see that. Can't do it in general, but that works when T2 is a polynomial. So there's many small details surrounding this that people knew awesomely in the 70s and 80s, and then people sort of stopped caring a little bit. But now is the time to care. So okay, let's talk about other hierarchy theorems. There's also a space hierarchy theorem, and the proof is the same. Basically, it's diagonalization, and it's better. It's easier and better. Why? Because this simulation is easier for space. If you need to simulate a k-tape Turing machine by a 2-tape Turing machine, and the k-tape Turing machine runs in space S of n, you can do it in space order S of n, and that's easy. So k-tapes, space S, you can simulate with 2 tapes, and space order S. Well, that's basically because the tapes, you can just put them all into one tape. There's a constant number of tapes, so you're only storing constantly more information. Yeah, you're all cramming onto this one tape, but that's okay. You don't have to worry about the fact that you need to go back and forth in the heads, because you're only concerned about your space, not your time. So you can basically cram it all together. Uh-oh, is that wrong? Yeah?
No, I was just wondering how do you measure space on multi-tape Turing machines?
Oh, it's just the sum of all the number of tape cells accessed. I mean, on each of the tapes. Yeah, just the total. It's not like the max over there. It doesn't really matter because of the constant factors, but it's, so I guess it could be the max over all tapes or the sum over all tapes, but we'll say the sum. Right. Good. And keeping the clock is fine because the clock is a much smaller space than you're worried about anyway. So therefore, there's a space hierarchy theorem. And in the space hierarchy theorem, let me just do it like this. Space hierarchy theorem. Let's call it S. And now it only needs to be at least log n. So remember, in space complexity, we don't charge. Usually the input tape is considered read-only, and we don't charge for that space. So it's actually very natural to consider space complexities that are sublinear. But log n is the least reasonable amount of space really to consider, because you need to keep track of a pointer into the input. It's hard to imagine any algorithm that doesn't do that. Okay, let me call it S1, and let S2 and be just big omega of, or little omega of S1. Okay. In other words, S1 just has to be strictly little o of S2, and that's just so that any big O on the S1 can be beaten by S2. And it has to be space constructible, which is the same definition here, except space. Okay, and then right, space, space. Okay, so the space hierarchy theorem is like slightly sharper than the time hierarchy theorem, is the current one we know. Like any T1 that's little of T2, there's more languages decidable in space T2 than space T1. Do you have a question? Yeah.
Oh, yeah, the space constructible definition is that work tape space, right?
That's right, work tape space. Yeah, you always only measure in space complexity the work, quote unquote, work tape space, like not the read-only input tape space. That's one reason why it's very convenient that we're working with multi-tape Turing machines. You know, that's the natural context for space-bounded computation. Okay, great. Okay, well, just like in last time, that's one paradise. But now we're going to go to non-determinism, and that'll make our lives a lot harder. But this, as I said, is an important theorem. So now we're going to talk about non-deterministic time and a hierarchy for it. So, okay, remember non-deterministic Turing machines. You know, they have this ability to like guess bits to their tape, and then that's fine. The weird thing is like your definition of when they overall accept, and it's asymmetric between like yes or no and 1 and 0. Like you say a non-deterministic Turing machine outputs 1 if there exists a set of guessed bits that make it end in an accept state, and otherwise it outputs 0. So there's an asymmetry there in terms of its like overall accept reject condition. So let's think about what would happen if we tried to do a time hierarchy theorem in non-deterministic time. Well, that asymmetry between the accept and reject is going to be the big problem. But let's delay talking about that briefly and talk about these other more minor issues that arise. And one of them is this. Okay, so what's the deal with if you have a K tape? These things are a bit technical, but again, this is the time in our lives when we'll talk about them. What's the deal if you have non-deterministic time and you have like a K tape time or n time t Turing machine, and you want to simulate it by a 2 tape or fixed number of tape non-deterministic Turing machine? What's pretty cool, as proved in 1970, is that you can actually do this in order t time. Okay, so you don't need the log t slowdown for this. And that's by exploiting the power of non-determinism, which you have. This is proved by Ron Book and Sheila Greibach and Ben Wegbright. And I'm not going to say, it's not very important, but it's kind of cute, so we'll use it. And I'll say the proof in words. I won't write anything. Basically, imagine you're simulating a K-tape Turing machine on a 2-tape Turing machine or a 3-tape Turing machine. Why can you not just sort of simulate everything that happens on the first tape, then simulate everything that happens on the second tape, then everything that happens on the third tape, up to the kth tape? If you could do that, you'd only get a slowdown of like factor k, and k is considered constant, so you'd be very happy. Well, the reason you can't do that is like you're going along, you know, simulating what's happening on the first tape, but like you're always in trouble because, you know, in order to understand where the first tape head moves left or right, you need to know what is the state of the whole Turing machine. And that depends on like what all the other k-1 heads are currently reading. And like you're not simulating those other tapes yet, so you don't know what to do. But you have non-determinism. So you just guess all the like Turing machine state plus what symbol is the head reading, which is a constant amount of information for every time step that you're going to do. So there's going to be capital T time steps, and at each time step, the heads are going to be, each head just reads some symbol, and the Turing machine is in some state. You just guess all that information at the very beginning, order of T time. Then you simulate all the tapes sequentially like this, assuming the guesses are correct. So you can simulate everything that happens on the first tape, because like you know, assuming your guesses about all the TM head symbols and so forth are right, like what to do on each tape. And then you just do that and see if you ever like encounter a bug in the simulation, like if your guesses were ever wrong. And if they were, you just reject. But if all the guesses were like miraculously correct at the beginning, then you'll notice that and confirm that, and then you'll just give the correct answer, accept or reject. So that was, okay, that's fast to digest in words, but that's the idea. You can do it. And we'll see this trick actually more than once, that like once you get to non-determinism, like things are actually kind of better because you can do some funky tricks like that. OK, so without saying more about that, let's put that in our pocket. And this was the thing that caused us to lose a log factor, right? So you might wonder, OK, maybe because of this, we can hope for like the dream hierarchy theorem, like we have for deterministic space. You might hope that like non-deterministic time t1 is the subset, but not contained in non-deterministic time t2, provided t1 is little o of t2. Okay, so that's something like that is always like the dream hierarchy theorem. We have it for space. For deterministic time, we lose a log factor. And we cannot quite get this. This is not known. And as you'll see, we can very, very nearly get this, which is good enough for our purposes, but not quite this. But there's a major problem in just trying to get this by repeating the proof of the time hierarchy theorem, the regular one. And this problem, as I alluded to before, is that basically, non-determinism is not closed under complement. Okay, so in D, the diagonalizing machine, which used to be on this board, you simulated Q for a while. And so far, so good. Like non-deterministic D can simulate a non-deterministic Q. But then there comes a time when you want to do the opposite of Q. And it doesn't work if you just like reverse accept and reject, right? Because in non-deterministic Turing machines, if you take a non-deterministic Turing machine and flip all its accept and reject states, that does not cause it to accept the complement language, right? So that doesn't work. And it seems to be like a critical aspect of the proof. So people were stuck on that for a little while in the 70s. Any questions about that issue or this issue? Yeah.
The certificate that you give to a non-deterministic Turing machine, is it always have to be polynomial time? Because it seems here like you would get a certificate that is bounded by O of t event. Is that problem of t events really big?
You should not think of non-determinism in terms of certificates. So there's a definition of NP involving certificates where like you imagine a Turing machine that gets some kind of certificate tape and then it tries to confirm it. But it's hard, but eventually you have to just like accept like the other non-deterministic model. So like there are no certificates really in non-deterministic Turing machines. It's just they can like guess as they go along, or they can. As I mentioned last time, you can also think of it as probabilistic Turing machines, which flip coins at each step, and you have a weird notion of when they overall accept. It's like if they have a positive probability of reaching an accepting state, you count them as accepting overall. Otherwise, you count them as rejecting. So the connection with certificates is that like you can think of like if a non-deterministic Turing machine overall accepts, you can think of like all the correct guess bits that caused it to reach an accept state as a certificate for the fact that it accepts. So in some sense, like the certificate length is kind of, when you're doing these things, it's kind of the same, or it's related to the number of guess bits that the non-deterministic machine used. But it's really helpful for just reasoning about non-deterministic time to just take the non-deterministic Turing machine model, like weird though it is. Yeah.
So for not to harp on this, for the two-tape NTM simulation argument for the k-tape NTM,
yeah.
Basically what you're doing is like for each time step, you non-deterministically guess probably not like where the head position, but just like what's at the head and maybe what's to the left and right of the head or something like that, like a constant amount of information per tape per time step.
That's right. I think you'll just need like what symbol the head is reading, but yeah, sure, throw in the left and right too, just in case.
See with the previous time step or something like that in some way, right?
Yeah, maybe. Yeah, I didn't think it through carefully, to be completely honest, but luckily some people did. Yeah, so you don't guess the positions of the heads. You just guess what the symbols the heads are reading. Maybe let's say what's on the tape to the left or right of them, and the state of the Turing machine, like in the state transition table. And that's a constant amount of information per time step. You guess all that like right at the beginning and write it to some like third tape or whatever, some fixed tape. So that's order capital T information. And that's like the guessing bits. And then after that, you act deterministically. No, you don't act deterministically because you're still simulating a non-deterministic Turing machine. So like when it does a guess, you also have to do a guess. Okay, good. Great. So okay, so this is a seeming problem for non-deterministic time hierarchy theorem. Like it's not closed under complement, so it seems hard to diagonalize. Before we get into fixing it, which will be the last part of this lecture, let's stall for a minute and go to the fourth possibility, which is non-deterministic space. And what's good about this is, see, non-deterministic space is closed under complement. That's a theorem which you may have seen before. I guess we won't cover it, but if you haven't seen it, you can take my word for it. It's a theorem due to Immerman and Selip-Cheney. And it's not trivial, but it's not horrible either. And it's in SIPSA, for example. And so great. So it's closed under complement. And so you can just basically use this reversing trick. This trick also holds up for, well, everything is easy with space. So this simulation is also fine for space. So we actually get the perfect, non-deterministic space hierarchy theorem exactly like this. So that's cute. Okay, now we have to, okay, this is perfect. In the last half hour, we're going to prove the non-deterministic time hierarchy theorem. And this requires a major idea to overcome this issue. And what is one aspect of the idea? One aspect of the idea is this. If you have a you can do the opposite of a time, let's say an n-time t1 machine in something like, to be imprecise, 2 to the t1 time. And even deterministic. So like if you have a t1, let's say a linear time non-deterministic Turing machine, if you really want to be a simulator that like exactly does the overall opposite of what that non-deterministic Turing machine does, you can do it in like exponential time. And you just do it by like brute force, deterministic, like enumerate, like try out all of its guess bits. It only runs in t1 time, so it only like guesses at most t1 bits. Or if you think of the probabilistic model, it only flips like t1 of n coins. So you can literally just deterministically spend all the time to like try all that out, see if it ever enters an accept state. And if so, that's when it overall accepts, and you can now reject. And if it never enters an accept state, that means it overall rejects, and you can now accept. So for example, using this idea, it's not hard to show that non-deterministic t1 time, their language is, their language is decidable in deterministic 2 to the t1 time, which cannot be decided in non-deterministic t1 time. So you kind of get like a hierarchy theorem where you have non-deterministic time t1 over here and deterministic 2 to the t1 time over here. That's not so great, though. Yeah?
Do we know for sure that n time is not closed under complement, or is that like unknown?
No, I guess it's basically the same as NP versus co-NP. Whether or not it's closed under complement, even with polynomial slowdown, is I guess like NP versus co-NP. So I guess we don't know it, but.
So it's not even known for other functions?
Probably for fixed functions, I would guess no. If you talk about like allowing some slowdown, then like I think like non-deterministic 2 to the 2 to the poly n time is like the same as co-non-deterministic 2 to the 2 to the poly n time, because like the running time is so big that like you can do this trivial slowdown even deterministically and like just have 2 different polynomials. You have like so much time over here compared to this one. But if you just want to like compare non-deterministic time t to co-non-deterministic time t, I don't think it's known and it's considered unlikely. Okay. So that's an idea. And we're going to use this idea in the non-deterministic time hierarchy theorem proof together with something called delayed diagonalization. And delayed diagonalization at a high level means you don't just try to, for each machine running in t1 time, you don't just try to, like, as a simulator, you don't try to differ it on one specific input, like the input that encodes the machine. You have like some big range of inputs that you associate to that machine. You only try to make sure you're different from that machine's operation on one of the strings in this very big range. Okay, that's a high-level description that probably doesn't mean much to you yet, but hopefully you'll sort of see what it means as we go along. Okay, so let me write down now the non-deterministic time hierarchy theorem. So it's really great. So let's set t1, let's say little t, be at least n, and let capital T be, okay, this is where it gets funny. So what we need is that t of n plus 1 is little o of t of n. So it's very close to the thing that we normally want, that t is like little o of big T. There's a slight difference between n plus 1 and n, which most of the time doesn't make a difference. Like if this is n squared, then n plus 1 squared is big O of n squared. So it's as if we had n here. But for some like super high running times, like 2 to the 2 to the n, like there's a big difference between whether you put in n plus 1 or n. But that rarely comes up. So basically, it's almost what we would like in life. Okay, so then there exists an L in non-deterministic time, capital T, which is not in non-deterministic time, little t. And for this proof, both t's need to be time constructible. But nobody ever kind of really cares about these hypotheses, so whatever, let them both be time constructible. It's fine. Okay, so this is the theorem that I want to prove in the rest of our time. Okay, and I'm going to give you a proof sketch because there's one main idea and then some fiddling of the sort of fiddling that we already had in the deterministic time hierarchy theorem. So for example, that issue about like, oh, you want like a Turing machine to be represented by infinitely many strings because like you need the big O or the little o to kick in. That's also present in this theorem, but I'm going to skip discussing it. We're going to like implicitly use this theorem without like really getting into any details, that you can do a simulation of one non-deterministic machine with lots of tapes by another non-deterministic machine with 2 tapes with only a constant slowdown. And I'll just give you the actual ideas in the proof, taking those for granted. Okay, so here I'm really going to define the language sort of directly, which is in this amount of time, but not a lesser amount of time. So, and it's actually, this is a bonus. It'll be a subset of 1 star. Okay, so it's going to be a unary language. It's fine. So all our inputs just look like n many ones for one, or the symbol 1. We'll just call this n. Okay, so we'll think of the n inputs as non-negative numbers, integers, encoded in unary. Okay. I should mention, by the way, that this proof was originally proved by Cook, but not quite as tight as this. And then it was made tighter by Seyfried, Fisher, and Meyer in '78. And then Jacques and Ming Li independently gave a nicer proof, which is the one we'll do now. Okay. So we still want this trick that we're going to consider the input to be the encoding of a Turing machine that we're going to try to diagonalize against. So we'll just use the notation that Mn is the non-deterministic Turing machine. It's basically encoded by the input n. So, but we'll take the binary representation of n. So we get a bunch of 1s and 0s. And we'll take that as the encoding of a non-deterministic Turing machine. Okay, so we're going to try to have an algorithm that diagonalizes against this mn, but not necessarily on this input 1 to n, on like some range of inputs. Okay, so we're going to consider all possible inputs to Turing machines, which in this unary convention are like called 1, 2, 3, 4, 5, 6, 7, 8, etc. And we're going to divide them into large intervals. So the inputs will be divided into consecutive and contiguous intervals, which I'll denote like this, L1 through U1, and then L2 through U2. These are ranges of integers. L3 through U3, etc. This is the beginning, so this is 0. This will be some very large number. This will be just U1 plus 1, and like this will be U2 plus 1. Okay, so it's just a sequence of consecutive intervals. And we'll come back to this later, but one point will be that Uj will be way, way, way bigger than Lj. Okay, that's way, way, way bigger then. Okay. Okay, and so as I said, instead of the diagonalizing machine trying to just differ from a given Turing machine Mn on the input n, it'll actually like find what interval n lies in and try to differ from m for that interval on at least one string within that interval. So it's trying to do a lot less than in the regular non-lazy diagonalization strategy. The interval is going to be so big somehow that like it'll have sort of time to implement this idea. So again, it's probably not clear what's going on yet, but these are some hints for what I'm about to say. Okay, so here, as before in the time hierarchy theorem, I'm going to define the language L, capital L, through the machine, and this is the board I'm going to write it on. So we're going to have a non-deterministic Turing machine D, which takes as input some integer n encoded in unary. So this is really like maybe 1 repeated n times, or some symbol repeated n times. But on input n, this is a high-level sketch of it. So first it's going to find the interval in which n lies. So it's going to find j such that n is between Lj and Uj. And as we'll eventually see, this part won't take up much time at all in the grand scheme of things. So consider that to be not a problem. OK, and now here's where it gets interesting. It's going to do two different things depending on whether or not n is the last number in the interval. OK? So most of the time, n is not the last number in the interval. And in that case, it's going to do something fairly simple. So if n is not equal to Uj, we're going to simulate m sub j, not m sub n, but m sub j, the Turing machine associated to the string, which is, the number of what interval this is. Not the numbers inside the interval, but if like this is the third interval that n is in, we'll simulate m3. Okay? Because basically we want to understand what m3 is doing on this interval, and what m2 is doing on this interval, and what m1 is doing on this interval. Okay? So the n kind of just tells us what interval we're talking about. But we don't worry about mn, we worry about the machine for the interval that n happens to lie in. So it's going to simulate mj. This is where the cleverness happens. On input n plus 1 for t of n steps. Well, you probably cannot read this, but anyway, for t of n steps. OK, so it's going to, n puts you into some interval, like the third interval. And the d is going to start simulating m3, but not on n plus 1. Which is some string or input that's also in this interval, because n is not the topmost guy. And that's it. Notice I did not say do the opposite. You do the opposite of opposite. You do the thing. You just really just simulate it. Okay, the special case is when n is the top thing in the interval. And what do you do here? This is where you use the idea. You deterministically, brute force, simulate mj, the Turing machine associated to the interval, but on the lowest guy in the interval, lj, for basically like log base 2 Tn of m of j's steps. So here I told you that you should do this simulation, d should take this amount of time, and here I'm saying, oh, actually, d should do this many steps of m sub j. But it has enough time to do that in capital T of n time, or O of capital T of n time, because of this idea. Okay, so like, as we'll see, I'll calculate this later, but like L sub j is like so much smaller than, let's say U sub j, that you have like so much more time, you could afford to do this like super brute force simulation. Oh, and there's one more thing, do the opposite. Okay? And we really can do the opposite of it because we're doing this, we're not using non-determinism to simulate non-determinism, we're using like determinism to simulate non-determinism in a brute force way. So we can really figure out exactly what the non-deterministic machine MJ does and like do its opposite. Any questions? Yeah.
So this means that MJ is being simulated on every integer because like you shifted the coverage interval. Is that the idea?
Yeah, I should have said that as well. But like this machine D does kind of, over all its inputs, it does effectively simulate, if you have some interval here, like 10, 11, 12, 13, 1 million, or some big number. That's a very big number, but that's OK. Yeah, like D will simulate, when the input is 10, D will actually kind of simulate this was probably maybe the second interval, so it'll simulate M2 on 11. And when n is 11, you'll simulate M2 on 12. And you'll go like that. And when n is this, the simulating machine will simulate M2 back on 10. Okay? And you kind of see that like, oh, now it's got like so much time. It can do crazy things like just brute force deterministically simulate M2 on that. And that is set up so there's like kind of a chain or a loop. That's what we'll do now. Basically the simulation will like kind of agree with, you'll kind of get like agreement all the way along this chain except at the end of the chain. So there'll have to be some disagreement somewhere in this loop. That was not too clear, but hopefully it'll be clear now. Okay. Okay, so as before, we're coming to the proof. So L, the language we care about, will be the language accepted by D. And the fact that it's in non-deterministic time, T of n is by design. Okay, and this we're implicitly using that book Greibach-Weinstein, I always forget the third guy's name, sorry, result that you can do these simulations with only constant overhead in non-determinism land. And for the last part, we're using this brute force idea. OK, so we have to now prove the second part, that there's no time little t non-deterministic Turing machine that decides L. In other words, any such Turing machine must disagree with D on at least one input. And in fact, you really need on infinitely many inputs to take care of this big O issue that was issue 1 with the first hierarchy theorem, but let me not worry about that either. It's the same fix. OK, so suppose for contradiction that M is time T of n. It really should be O of T of n, but I'm ignoring that fix. Non-deterministic Turing machine such that it agrees with D on all inputs. Okay, so this is our assumption for contradiction. That this time little t machine agrees with D everywhere. Okay, so assume this. M does the exact same thing of D on all inputs. OK? And let J be the J such that this hypothetical M is Mj, according to this notation. OK? And we're only going to worry about this condition and what is going on with this M on the jth interval of inputs. OK. So let's just slowly go over what this fact means vis-a-vis the description of D, which we know up there. OK, so just for strings within this interval, so we'll start with the one at the bottom. So by assumption, M on the Lj equals D on Lj. OK? But what does D of Lj do? Well, it simulates M sub j, because Lj is the input. So first it looks to see what input interval it's in. Of course, it's in the jth interval. And then it says, OK, I'm going to work with M sub j. And M sub j is M. OK, so it figures out the right Turing machine we're talking about. And it simulates it, but it simulates it on Lj plus 1. OK, that's the catch. See, Lj is not the last point in the interval, so we're in this case. And n here is, in that notation, is Lj, so it goes to the next one. For how many steps? Capital T of Lj steps. OK? This is where the fancy counting comes in. So in this imagination, n in that notation is L sub j. Actually, I guess it's always, yeah. So you always go for T of n steps. So that's big T of L sub j steps. Now, this guy, by assumption, this assumption is takes or requires little t of Lj plus 1 time. And that's why we need capital T of L to be little omega of little t of Lj plus 1. OK, so this is precisely, oh shoot, it's no longer in here. It's precisely where, in the time hierarchy theorem, we have this condition. Little t of n plus 1 should be little o of big T of n. OK, this is precisely where this condition in the theorem is coming up. So by assumption, this is little o of this. So this is enough time to simulate this amount of time. OK, good. So that means we have enough time. So this simulation succeeds. I mean, it finishes and everything. And we don't do the opposite here. We just do what M sub j does. So what we conclude is that, therefore, D Lj is equal to M of Lj plus 1. So this is the first step in this little chain here. So we have this. And now we have this. OK, so actually, if you want, you could imagine putting these two things together. And we actually get that M does the same thing on Lj as it does on Lj plus 1. So let me do one more step of this game before we skip to the end game. So good. So by assumption, again, M equals D everywhere, supposedly. So by assumption, M on Lj plus 1 equals D on Lj plus 1. OK, but again, we'll ask ourselves, well, what does D do on Lj plus 1? Well, it's going to be the same ballgame, right? It simulates Mj. Let me write it. It simulates M sub j because its input n equals Lj plus 1 is still in the jth interval. So it's still working with, it still simulates Mj, which is M. But it does it on Lj plus 2 for capital T of n steps, and now n is this, so Lj plus 1 steps. Okay, and now we use again, this by assumption finishes in T1 of Lj plus 2 steps. And we use our main assumption in the theorem that this is like little o of this. So this simulation has time to finish, and it works fine. And so therefore we get d Lj plus 1 equals m of Lj plus 2. Okay, you see we've extended this chain further. So now m Lj plus 1 also equals m Lj plus 2. Okay, and this chain goes on and on and on.
Question.
Yeah.
So when you say that m of n is equal to d of n,
Yeah.
that means that if both of so that for all that there exists some random coin flips that leads both of those Turing machines to succeed or to accept, or for all coin flips both of those machines they could do not accept, right?
That's right. So when
Here we're just simulating that. So I mean, like we cannot say that m of Lj is equal to d of Lj, right?
No, we can. So what I mean is, okay, so yeah, what I mean by this notation is when these are non-deterministic Turing machines is what is the overall output or overall accept reject of this machine run on this inputs. And that relies on the definition of what it means for a non-deterministic Turing machine to overall accept or overall reject. Or think of it as the non-deterministic Turing machine to output 1 overall or output 0 overall. And that's a funny definition, like it overall outputs 1 if there exists some set of guesses it makes that leads it to an accept state, and it overall outputs 0 if all guess bits lead to a reject state. So yeah, we don't necessarily know that like D sort of, in this, we don't know how it works. We don't know at all that like D does M or like has the same guess bit behavior or anything. We just know that like the overall output of D in this weird sense of what it means for a non-deterministic Turing machine to have an overall output is the same as what it is for M. Okay, yeah, maybe we should, I guess actually, in fact, in the next lecture, I might like review a little bit non-determinism. It takes a little thinking about. Okay, I'm almost done, so let me just finish this punchline. Okay, so if we repeat this argument until the end, we get that d on uj minus 1 equals m on uj, and that equals d on uj. And that's the last place we can sort of do the argument, because d on uj minus 1 sort of simulates m up here. And by assumption, m equals d everywhere, so these are equal. But if we put together all these boxed things, everything is equal, and so it goes all the way back to the beginning, and we get that this equals m of Lj. So m is actually has a constant output, same ultimate result on all inputs in these intervals. But now we're going to get a contradiction by asking, what does this do? Well, this is where we finally fall into this case. We still work on Mj, but we simulate, it simulates, Mj on the lowest guy, Lj, for log t of n steps, t of uj steps. Okay, since capital T is, it's at least n, this is at least, I'm being slack here, this is at least log 2 of u sub j. Okay, and it does the opposite. Okay, and now we just have to make sure that little uj is chosen way, way, way bigger than L sub j. And we can freely choose this. So we can like take, I don't know, this to be 2 to the the running time of mj on little j, I don't know, cubed just for safety. So that this amount of time, log of u, is now the cube of t of little l of j. So it's more than enough time, because like this actually runs in t of L of j steps by assumption. Okay, maybe you're doing a deterministic simulation here, so you might have to worry about the tapes or whatever, but like, you know, you're doing it for like this many steps, so you got yourself covered. Okay, so this is all just cooked up, so this will succeed. So d of uj succeeds in doing the opposite of mj lj. Okay, so then we get this, and that's a contradiction. Okay, well, that's the end of the proof and the end of the class. If you have any questions, I guess maybe ask them on Piazza, or I'll be around for a little bit.